Hi everyone, thanks for coming. Our speaker today is Dr. Vincent. He's a postdoctoral research fellow at Princeton University. Vincent finished his PhD in 2006 from ETH Zurich, and he'll be talking to us today about field-based routing and applications in wireless ad hoc networks. So I'll let you begin.
Thanks for this introduction, and thank you for coming to my talk. So I will be talking about field-based routing, which is a model I developed mainly during my thesis, and how actually you can apply it to solve different routing problems or networking problems in wireless ad hoc networks. So let's start with the motivation. Well, we're observing more and more emerging wireless ad hoc networks in different contexts. Certainly in the area of sensor networks, we have seen deployments of ad hoc networks, but also in vehicular networks where people try to connect cars together to provide useful service to the driver to prevent accident, also to avoid the traffic jams. But also mesh networks, which can be seen as ad hoc networks, where the idea here is to connect base stations in a city or in part of a city to provide internet services to users. And also we have seen social networking popping up where people with their mobile device connect together and want to exchange files, whatever. So this talk is about routing for wireless ad hoc networks, and here's just a small list of all the routing challenges that we encounter in ad hoc networks that are not present in fixed networks like the internet. And for example, one big issue is that we have wireless links and also hence fading channels. So the channel is changing over time, even if there is no mobility. The link condition may change over time and produce packet losses. So we might have node mobility in the network, so nodes move around and the network topology changes frequently over time. Then we also have wireless interference. We have internal interference from nodes communicating at the same time, interference with each other, but also external interference from other radio sources that may be in the neighborhood. Then there are also other problems like scalability. If you want to build large networks, we might have limited resources. If we're talking about small sensor nodes, they might only have limited computing capabilities, and the network layer must be able to cope with this. And also disruptions. We cannot really assume all the time a connected network because the nodes might move away and disruption might form. But in this talk, I really want to focus on these two challenges, which are fading channels and the node mobility, and how we can achieve robust routing with these conditions. So this is the outline of my talk. I will first introduce you to the basic model of field-based routing and how it works. Then I will show you how to apply the model for a robust AnyCast routing strategy, which we call density-based routing. And then I will also apply the same model for another scheme, which to improve the robustness of Unicast routing. And this scheme I will call it link diversity routing, and then I will conclude. Okay, here is how field-based routing works. Let's start with a very simple example. We have a source on the right and a destination, and the source wants to send a packet to the destination. So what we do, we model the destination as a positive point charge. Well, here I will use the analogy to electrostatics using charges, but as we will see later in the talk, the model itself is not really bound to using electrostatic analogy. We can just think it as a field, but for as an illustration purpose, this analogy, we'll start with this analogy. So we have a positive point charge, and what happens if we have such a charge in space? Well, around this charge there will be an electric field which can be described using the potential field. So here we have the charge, and the potential field at the node which has the charge will be maximal. So the potential distribution will decrease over the distance. So the potential value of the nodes will be as shown here on the figure. And when the source wants to send a packet, we model the packet as a negative test charge. And what happens? Well, if you have a positive charge and a negative charge, since they have opposite polarity, the negative test charge will be attracted by the positive charge. And this is done like this. Well, at each hop, the test charge will be forwarded or will be attracted towards the steepest gradient. And here the gradient is towards the left, so there is an attraction, a force here. So the packet will actually diffuse to the destination by following the steepest gradient at each hop. So this is really how the basic model works. We can think of having multiple destinations. Well, the concept remains the same. What changes is here we have two destinations, so we have 2 point charges. And what we plot here is actually the resulting potential distribution, which is simply the linear superposition of the influence of both charges. So now if we have a source here, and the source sends a packet, what happens? Well, the packet is attracted. There is a force on this negative test charge, and the test charge will be attracted towards the steepest gradient, which is here towards the left, because the gradient here is larger than towards the right. So the packet will diffuse in this direction. Excuse me. So if you notice, well, the source is actually 2 hops away from the left charge and 3 hops away from the right one. And as you can see, the packet is forwarded along the shortest path. And this is one property that we can achieve using field-based routing. I'll come to that later in a few slides. Excuse me?
There are 2 destinations. It's only one.
Right.
Doesn't have to reach different destinations.
No, you're right. So here I'm really, the goal of the routing was actually to reach any destination. It's like AnyCast routing, where you send a packet and it should reach one destination. Yeah. So here's the big picture. If we have a network topology, as we have here, and we have the black nodes as possible destinations, they will create a potential field with peaks at the destinations, and the potential distribution, the potential values of the relaying nodes will decrease depending on the distance. The farther you are, the lower the potential value.
What if the source is exactly equidistant from 2 destinations? It will not go anywhere, right? Because it will be a local minima there.
No, there will still be a steepest gradient.
No, but can you go back to certain previous? Okay, in this case, let's say you have 5 nodes in between those 2 destinations.
Mm-hmm.
Let's say, and it is the charge, negative charge is exactly in the middle node.
Mm-hmm.
So then it will be in the minima, right? It will be, there won't be, so it will be equally attracted towards both sides.
It will be equally attracted to both sides. So, but since our approach is actually following the steepest gradient, so there are multiple steepest gradient, we'll just take a random one because they actually they have the same gradient. But so the approach is really always following the steepest gradient. If there are multiple ones, choose an arbitrary one. So the big picture is actually like this. So you will have a network topology and the peaks as discussed before. And what results is a potential field that would look like this. And when you send a packet, it will...
How does transit determine? All the destination equals trans?
Excuse me?
All the destinations should have equals trans over here?
I didn't acoustically understand your question.
So I mean, so all the destinations are supposed to have equals trans, equal potential of the height?
Right. So here they have the equal potential. So, but the potential value of the destination, as we have shown, is a very high peak, so it goes to infinity. So the potential will be very high, or infinity. Well, you cannot describe this in terms of, so it will be the maximum possible value, and then it will decrease. In this example, all have the same capacity. We'll come to that later, how you can actually model different capacities for depending if you have different destinations. So the basic concept, well, is the big picture. The packet will simply diffuse along the steepest gradient until it reaches the destination. Okay, so here is just a summary of the concept. So what do we need for the routing to work? Well, the preconditions are that we actually need a potential field with only maxima at the destination. And so if we have only maxima at the destinations, means that there are no nodes in the network which have neighbors with have only descending gradients unless there are destinations themselves. So if we manage to have such a field and we route along the steepest gradient, then as a result, we get two nice properties. We get a guaranteed delivery. We can actually prove that a packet from any node in the network will eventually reach a destination. And a second nice property is that the routing is loop-free, because we make sure that we route along an ascending gradient. That means that a packet cannot really go back the hill and come down, and so this way we cannot have actually loops in the routing. So you might think of, as I mentioned before, it's possible actually to model shortest path routing with the approach with field-based routing. And if you look at, this is a very simple example, you have a destination, you have a source, and traditionally, if you take, for example, a distance vector routing, you will have the distance 0 at this node. At this node, then the nodes that are 1 hop away, they will have a distance of 1, and these two nodes will have a distance of 2. And if you take traditional shortest path routing, the forwarding would be like this. This is the forwarding path, and the source would send a packet towards the destination along this path, because it's the shortest path.
Are you assuming that in the ad hoc network, the source knows the overall topology of the network at any given point in time?
No, I don't assume this right
Then
now.
how do intermediate nodes get the knowledge of which direction the steepest gradient is?
I will come to that next slide. So just here to show the analogy of shortest path routing and what you can do actually with field-based routing, but I will come to that later. So actually what we do with field-based routing, well, we model, we have a potential value at the destination, which is a peak, and then it decreases over the distance. And if we model the potential values of the nodes like this on this picture, we'd actually get the steepest gradients, which look exactly the same as with shortest path routing, and it simply means that we can actually model or instantiate shortest path routing with the model. But what do we gain from that? Well, we can actually, we do not restrict ourselves to the shortest path solution, but we can also look at different solutions. For example, that the source node sends, now if we assign the potential values according to this picture, the steepest gradient of the source will no longer be here because this potential value is smaller, so the steepest gradient will be towards this node, and the source will actually send its packet here. So for this example, it might not be, you might think it's not really useful to do that, but I will show you that in some cases it's really useful to not consider the shortest path, but all the alternatives. For example, for AnyCast routing. So let's consider AnyCast routing, and how AnyCast routing is implemented today. Well, it's based on shortest path. So here in this example, we have the group members. So the goal of AnyCast routing, as I mentioned before, is to send a packet, and this packet should reach any group member, anyone, it doesn't matter. So traditional AnyCast routing will simply assign a value of all the relaying nodes according to the distance to the closest group member. So here, for example, this is a group member, a black node. The relaying node has a value of 1 because it's 1 hop away. This one has a value of 2, and accordingly I just numbered the distance of all the nodes.
How would you establish these numbers, and how would you know that this destination has 2 hops to stay?
So traditionally, for example, if you use a distance vector routing protocol, they will exchange periodically distance information. So this node will actually send periodically a message saying, well, I'm the destination, so I send a value of the distance of 0, and then this node receives this message, and then it knows, oh, I have to add 1 because I'm 1 hop away.
When you are using distance-based vectors, and if you're using RIP as the underlying medium, then why can't we straight away do the routing on RIP? We already have everything set up with the distance-based protocol. Why can't we directly go with the distance-based routing protocol? Why do we need to go for
I didn't. What do we need to what?
If you're using the distance-based thing, I mean, you are exchanging packets to more than neighbors, right? You know, in order to know the destination, you just exchange some distance-based packets. When you have this information, then why can't you extend this to use a normal RIP routing protocol? Why do what is the advantage I will get if I go through RIP routing?
Well, I'll come to that. So I'm just explaining how it works, how the traditional routing works. So the next slide will show you the advantage. So here you have traditional shortest path-based routing. This is how you do it today, without field-based routing. What happens, the sender here is actually 2 hops away, and he will send its packet towards this group member because he thinks that this node is closer to the group member here, and these two are 2 hops away, so it will send the packet towards this group member. So the problem with this approach is actually when, for example, this group member disappears, or it moves away, or the link here becomes unavailable to fading or whatever. Well, this intermediate node cannot relay the packet anymore, so it drops the packet. And actually, what you could do, an alternative way, what you could do is by assigning a field in such a way that the density of the group members is reflected in the forwarding decision. And this you can, for example, do with field-based routing, but by assigning a potential value of the potential value according to the density that you have here. So here, if you look carefully, you have 3 group members that are close together. So they would consequently create a higher potential values in their surrounding than this one, which is here alone. So here, the sender now has the option to send here because the steepest gradient points towards the blue arrow and no longer here. Simply because here we have a higher group member density.
How do you assign the field? Who assigns that? The field values?
I'll come to that on the next slide. So this is just to show you. This is actually just to show you what's the benefit of it. So here I send to this. I follow the steepest gradient, and I will get here. Now, what happens if this group member dies or moves away or whatever? If there is a problem, then the relaying node has another forwarding opportunity. Now we can actually forward the packet here, and this was not possible before. This is actually the benefit. So your question was about how to actually create these potential fields, and how we do it is actually using an analogy from electrostatics. And if you take the electrical potential field, it's actually defined as such. Here we have the potential at the position R, where R is a vector in 3D space, and it's the sum over the influence over all charges you have in the network. You have all charges you have. It's not the network. And here, this term here, phi, the potential of the charge J, is actually a constant times a charge divided by the distance between the location R and where the charge is located. So this is how it works in physics. Now, our model is pretty similar. What we propose is actually to model the potential at a node n according by taking the sum over all the group members we have, where this term here now represents a constant times the capacity of a member divided by the distance between a node and this member over an exponent k.
What exactly do you mean by capacity?
So the capacity here would be the charge, and in our model, actually, the capacity would be the capacity of the group member. So if you consider, for example, AnyCast, you might have different group members, which might have different, depending on what you want to achieve with AnyCast. For example, if it's a gateway that you want to reach the gateway, this could represent the capacity of the link that the gateway is attached to another network. Or it could, if you want to represent the service with as a group member, then it would represent the capacity of the service that you have. So
just a number that you said? Capacity?
Yeah, it's just a number.
It's somehow proportional to the bandwidth available to that network.
If the service is a bandwidth, it's about a network service, then it could be proportional to that. If it's another service, then it will be proportional to the service that you provide.
Okay, so regarding this formula, shouldn't this QJ be the minimum capacity across all the hops? Like if you have a very high bandwidth gateway, but all the hops to the gateway are low bandwidth, then your QJ cannot be the bandwidth of the gateway.
No, this is actually the capacity. It's not I didn't mean by that the capacity of the links towards the gateway, but I meant if it's a gateway, the service is actually providing a connection to the internet. Or if it's another service, then it's if a computation service or whatever, then it would be, you would actually model the charge using this value here. It must not be a link capacity also, it could be the capacity of your service. So what's the difference between the electrical potential field and our model? Well, first, the electrical potential field is continuous, whereas our model is discrete. You have only a potential defined at the network nodes. And the second difference is that here you have a law that is according to an exponent of 1. So the distance is to a power of 1. And here we use a variable exponent to actually look at different, to actually explore the whole space that we have. So we do not want to restrict ourselves to one possible solution. And as I mentioned, this distance here is actually the distance between the group member and a node. So, and in our work, we'll actually consider the distance in number of hops. So you would actually know, in order to calculate your own potential value, you would actually need to know the capacity of all the services and your distance of yourself towards to this group members. So this is actually what you know. You do not need to know anything about the topology, the network topology. You just need to know the distance, how far you are from this. And this is typically what you need. What you have if you take a distance vector routing protocol, you always know the distance of all the nodes towards the destination. So this is not much more information that we require here.
So this is just the geographic distance, right?
Now, you could actually you could. I mean, in the model, you could actually use any metric here. You could take the geographical distance if you want to. But in our work, we actually didn't use the geographical distance, but we took the distance, the network distance, which means the number of hops. But you could also consider the transmission delays, and you could also put that. So this is actually your routing metric that you will have at the end. Depending, if you want to minimize the delays in the network, you would put here the delay, so the distance in terms of delay. If you want to minimize the geographical distance that your packets take, you would actually use this as a metric. And in our work, actually, what we considered so far, we didn't explore all the different possible metrics. We just looked at the network distance in terms of hops. So here is the exponent k, and on the next slide, I want to show you what it actually matters when you use a different value of k to determine the potential value. So here, what I plot is actually the distribution for a value of k equal to 1. So this is the same as the electrical potential field. And here, what you can see is a very simple example. You have a sender here, you have one group member here, and then you have two group members here. And the left one is 2 hops away from the sender, and the two right ones are 3 hops away. So the red curve actually represents the potential distribution created by the red group member. Then you have the blue curve, which represents the potential distribution of both together, of both these two group members together. And if you plot the overall potential distribution for these three group members, which is the linear superposition, you get the black curve, which represents the potential field for this AnyCast group. And now the sender, what it does, the sender sends its packet along the steepest gradient, and here, if you evaluate the gradient, it's steepest towards the left. So here, this value is higher than this value, so the packet will diffuse towards the left. And this is actually along the shortest path, because the sender is 2 hops away from the left group member, which is 2 hops. Now let's do the same. Let's consider the same network topology, but with a different value of k. So here I use a value of k equal to 0.3. For the red service or the red group member, the potential distribution changes slightly, so it's not exactly the same. It has this shape. For the blue two group members, it has this shape, and the overall potential distribution now has this shape. And if you look at the steepest gradient at the center, it is now in the opposite direction. It is towards the right, and here we have actually two group members that are further away, but the packet is forwarded in this direction because there are more than towards the left where we have just one group member. So as before, using a value of k equal to 1, we could have shortest path routing. Now we have actually density-based routing. Packets are forwarded towards the highest density. And actually, by looking at the whole space between the whole space of value of k, so we consider value of k between 0 and infinity, and here we plot the result for very small values of k, 1 exponent minus 0.5, and here 1000. And what we plot on the y-axis is actually the change of steepest gradient normalized. What it means, what this metric actually means, is how the steepest gradient changes at the intermediate nodes compared to the shortest path. So if you have a value of 0, it just means that the forwarding results in shortest path routing. And if you have a value greater than 0, it means that some gradients have changed in your network, and you do no longer do necessarily shortest path because things change. So here, so as we can see, the value of for large values of k, the value is 0, which means that in this region, when we use such values of k, we get actually shortest path routing. On the other side, when we use very small values of k, we get something like pure density-based routing, which means that the distance between the nodes in the network and the group member and have no influence on the routing decision. So the routing is purely based on the density of the group members we have. And in between, we have interesting solutions, which is actually a combination of proximity and density. So here, when you use values of k between 0.1 and 100, you actually get a routing that is characterized by a combination of going towards the closest group member and going towards a cloud of group members. Right, so this was for a particular topology. So depending on the topology, you might get different values, but what this plot shows is actually that there is a saturation point where you get pure density-based routing. There is here a region where you get shortest path routing, and you get something in between. So for a different topology, a different number of group members, the plot might shift towards the left or right, and also the density might change. But you still, for any topology, you have these regions.
Is this a system parameter?
Yes, so actually it could be seen as a system parameter that you can tweak, so to get the routing strategy that you want to have. So if you take field-based routing and you want to have shortest path routing, you could set use a very large value of k to determine your potential values, and you could guarantee that the routing is always along the shortest path.
Features were topology dependent. That makes it like, if I don't know the topology of routing beforehand, like setting a k would mean shortest path routing or something else, which I don't know, right? So like,
Right.
something that you want or something is problem.
So your point is that you don't know the transition periods here?
No, you don't know the topology before. Right? This was, correct me if I'm mistaken, this is for mobile, with trading, etc. So if I set the k value, it turns out I might have a short path routing, or it turns out I might have some pure density-based routing kind of thing. Is it like something that optimizes something else other than these dimensions?
Yes, so depending, I have results to show actually that the robustness of the routing depends on which strategy you use. So you could think of it in two different ways. One way, what we initially thought of was actually having a parameter k that you can tune in your system depending on the mobility you have. Because it came out that the density-based routing, I will show this on the next slide, simulation results to consolidate this, but it's actually, it shows using density is rather interesting when you have mobility. I also highlighted this introduction. So we initially envisioned this as when, if you have no mobility in the network, you want to do shortest path routing, because then you minimize the delays. I mean, this is obviously a good choice. And if you have a lot of mobility in the network of the links, you have a lot of fading, then you would actually tweak this parameter and do more density-based routing because it will increase the robustness. At the end, we actually came to another conclusion that let me continue.
Okay, before you go, I have a general question.
Mhm.
I'm trying to understand, this is really focused on trying to understand the intuition behind this. So, in general, if I do sum of 1 over d raised to k, where d is the distance, right,
Mhm.
I will get this behavior. That's what you're doing.
Yes, exactly. So I'm doing a sum
Of
the
d raised to k.
Right,
Q
right.
is not important, right?
Right. I assume you can assume here for this result all the Q are identical, so I set all to 1, and this is just having this effect of the sum over 1 over the distance exponent k. Exactly.
Now, is that the k, by using k, right, you're basically weighting the distance less and less.
Right.
Right?
Exactly.
So in this case, the only other option for you to do is it's either shortest path or density. So by weighting k, by weighting your distance less and less, you're basically biasing the decision towards the other side.
Exactly.
That's what this is showing.
Exactly.
Okay.
Exactly.
Now, if you have more than 2 options, have you thought of that? But that's a different discussion. If you have here, you have density and distance and density.
Mm-hmm.
If you have more than 2 options, how do you do that?
That's a different story. Okay, so now we have actually this parameter key that we can actually use to study different routing strategies. We can actually instantiate with the same model using field-based routing. We can actually instantiate shortest path routing, pure density-based routing, and combination of those. Now the question is, what does it bring us? And here I've got a result from simulations where I actually look at the robustness of the routing. And actually on the x-axis I vary the node speed, so the higher the speed, the more dynamics. For these simulations I use the random waypoint mobility model. I also use different mobility models, which I won't show in the presentation, and also when the network is static and we have fading channels. But the trends remain the same, so it doesn't really matter which model you use. As soon as you have links that break, you will have this kind of behavior for the different strategies. And on the y-axis, I plot the packet delivery ratio, which is the number of packets sent versus the number of packets, received versus the total number of packets sent. And what we can see here, well, if we have actually node speed of 0, there is no mobility in the network, but all the strategies perform the same. So you get a packet delivery ratio of 1. But as soon as the nodes start to move, the density-based routing schemes, or pure density, here the blue line is pure density, outperforms shortest path routing. So shortest path routing, which is here instantiated with a value of k equal to 300, where you get actually the worst performance.
How are you modeling the loss of packets? Is it because of broken links or fading links or what?
Well, I modeled it as right. It is modeled by having a node where it wants to forward the packet toward the steepest gradient, and this node disappears, so it will try another gradient until there are no steepest gradients anymore. So actually, then you cannot forward the packet anymore, and then you drop the packet. This is similar to IP routing. So you have a set of forwarding links. You try your preferred link, and then the second one, third one, where you do not have any forwarding links left, then you drop the packet. So it's the best effort. Right, because you have mobility in the network, links are disappearing when 2 nodes move away. Links are reappearing when nodes come back together. So actually, the conclusion is here that density is robuster. So you get the higher packet delivery ratio. Now let's look also at another metric of interest, which is actually the path stretch. So it's quite nice to have a routing that is more robust, but if you if you have to go a very long path to reach the destination, then you have a higher delays, and this is something that you certainly don't want to have. So here what I plot is actually for the node speed. On the x-axis, I plot here on the y-axis the average path length that the packets have to take. And if you see, as you can see here, the pure density-based routing has an increasingly, a significantly higher path stretch. So the packets have to take a larger number of hops than shortest path routing, which is here around the 3.3 hops on average. But if you consider a value of k equal to in the range of 1, so for example k equal to 3, you can see that the robustness was very close to pure density, and if you look at the path stretch, well, it is very close to shortest path. So actually the conclusion is here that the best trade-off you get is actually using values equal to 1, close to 1, because then you actually profit from the robustness properties of density-based routing, but you do not induce a higher path stretch than shortest path routing, so it's the best trade-off.
Are all the mobiles, all the nodes are moving with the same velocity?
We perform different simulations. I'm not quite sure on this plot, but I think we also did simulations where the node at different speeds. So
I was just wondering if things are moving around and the density is also changing. Right?
The density is also changing.
You said the links appear and the disappear, so the topology is changing. The density of the member groups is changing. So are you updating the potential field as they move?
Right. So I'm updating the field as they move also periodically. So every group member will periodically send an advertisement saying, "Here's my here I am," and then this propagates over the network. And this is actually used, these advertisements are used for every intermediate hop to calculate their own potential value. This is a repeating process.
Just wondering if there's some convergence issue there, because every time the topology changes, you need to update the field, and the field is you're using as input for your routing algorithm. So
we don't update the field every time the topology changes, we just update it periodically. So there is no, so the topology might change, but you don't have you didn't update your field, so these links just disappeared, are no longer available.
I have a question regarding how are your receivers or possible destinations distributed in the area over which you are running the random waypoint model? Because if I say k equal to 1 is the best trade-off, so in case I have the probability of finding a larger group at a given distance is the same as the probability of finding an alone node at that distance. Say I have one node at a distance t with the same probability as I have a group of 2 at a distance t given your simulation. Then it's always good to go with k equal to 1 because the 2 nodes will give you a higher whatever the metric to have, right? Higher field. But in case the probability of reaching a group is if the group of 2 nodes is much farther than the single node in your simulation, that is, okay, the way your nodes at the destination are distributed, then probably you'll always end up with sending to the single node because the metric for the single node will be higher. So it's like, are you assuming that the possibility of finding a group is as good as the possibility of finding a single node, like you have equidistant groups and single nodes or large groups and small groups from the segment?
Exactly. So this is what happens when you use a value of k equal to 1, because as I showed on the slide before, you have a combination of proximity and density. So at a certain point, there will be the two solutions will have the same probability. So it would be going to a group which is at a certain distance will be equally good as going towards a closer one, which is alone. So exactly. So but actually you can actually play with it. That's what the graph shows. By using a very small value of k, you get the strategy where you will always go to, you don't account for the proximity of the group members. So this information is not really used in the routing decision. It's only the density. Yes.
yeah, I think so.
Yes. Yeah.
Did you assume the channel error?
Yes, so for this simulation, I think there is only mobility, but then we have also the simulations which have a very similar trend, where you have static nodes, and then you have fading, which gives you packet errors. But it really doesn't matter. As soon as you have unpredictable.
How many nodes that the number of nodes is the number of destinations?
For this, it's around, it's between 200 and 500 nodes and 10 destinations, something like that.
And the total number of nodes are our destination. I believe that's for multitasking.
Excuse me?
It is for multitasking.
It is AnyCasting.
So single transmitter and multiple receiver, right?
It's a single transmitter, multiple receiver, but just the packet must just arrive at one. So this is, for example, for service discovery. So if you have multiple services, you're interested in one service. AnyCast is, for example, a useful delivery mechanism to find the service. So you don't want to reach all of them, but just one of them. Okay, so what I just showed is one way to increase or to do density-based AnyCast routing using the analogy of electrostatic fields. What I will show next is actually a different approach, which is for Unicast routing, and that is no longer based on the electrostatical analogy. So here is the motivation. If you have this network topology and you have a source here and a destination here, and here are the paths in your network. So again, if you have actually two options. You have a shortest path, which is the 3 hops on the upper path, and then the alternative would be to have a longer path, but which has a higher link diversity. So I call this link diversity by means of having here more options, more links towards the destination. So here, if you go along the shortest path, what happens is, again, if you have a problem in the network, a link breaks or destination moves, the intermediate relaying node has here on this path, it has no option. It will actually have to drop the packets and it cannot do anything. On the other side, if you consider routing over a longer path, but which has a higher link diversity, then if a link breaks, it's not so bad because this intermediate node has actually another forwarding opportunity, and it can actually proceed for the forwarding and the packet will eventually reach the destination. So the question here is really how to exploit this or how to model and how to express this link diversity in order to not choose the shortest path, but to choose the links with the higher link diversity. And again, we base ourselves on an analogy from physics, but this time it's not the electrical field because it doesn't have this property, but it's rather the temperature field that is actually created by heat sources. So here's an example. If you have a heat source and you consider the heat that propagates over, assuming that these are isolators, and you consider the heat that flows here. Here you have on the left side you have actually 2 diffusion paths, and on the right side you have actually 4 diffusion paths. And if you consider the heat flow that comes here out, it will be higher on the right side because you have more diffusion paths. So this is how it is in physics. So how can we exploit this? Well, it seems pretty straightforward to model actually this diffusion path or here as links and the intersection points as nodes. If you do that, you might get the same property as you have in physics, and you might exploit the link diversity. So, so how is actually the heat or the temperature field defined? So actually the heat potential, it follows the Laplace equation, which is here. So that's the heat equation, and the heat equation actually defines an unlimited number or an indefinite number of solutions, and so an exact solution is only defined when you with the given boundary conditions. And logically, we define the boundary conditions as having the destination as we define the boundary condition at the destination of value of equal to 1, and the temperature or the potential at the source of a constant temperature equal to 0. So here, actually, I computed the solution of the Laplace equation for this simple network topology. So here, again, we model the destination as a heat source and the source as a constant temperature, having a constant temperature, which is the boundary condition. So what you get is something like this, and here you have, if you recall our example from the previous slides, we had this path. Well, it is now 3 hops here, and here you have another path which is also 3 hops, but it has a higher link diversity. And if you consider the steepest gradient, so using the same forwarding mechanism as before, you would actually route towards this path because the temperature at this node is 0.47, which is higher than 0.33. So you would actually choose the path with the highest link diversity.
How do you compute these numbers?
Well, actually, I have to find a solution that follows this equation, and there is actually different ways to compute these numbers. So there are analytical methods to do it. But there is a very simple and very straightforward method, which is called the finite difference method, to calculate these numbers. And what you actually have to do is just calculate or determine. It's an iterative method, so you do multiple iterations, and you define your temperature as the average temperature of all your neighbors. So if you look here, this value here is actually the average over this temperature and this temperature, and this temperature here is an average over this temperature and this temperature. So if you look, all the nodes have a temperature which is actually the average of the neighbors. So by doing that iteratively, the finite difference method says, well, do this multiple times and you will come up to the final solutions. But actually there are multiple ways to calculate the solutions. So, well, actually regarding shortest path routing, I mean, if you have multiple paths which have the same link diversity, but the path length is different, the approach here will give you the shortest path. So here we have one path with 2 hops, one with 3, and one with 4. And if you do these computations, the steepest gradient will be here, and it will be along the shortest path. So actually, that's a good property. If you have a path of equal diversity, you still get the shortest path. So that's what I mentioned. That's what I mentioned before. How to actually calculate the temperature at the individual nodes, which have to solve Laplace equation. Well, here that's how the finite difference method works. Usually, if you want to calculate the solution on a plane, what you would do is you would actually span a grid on the plane, and then you have the boundary conditions which I have not plotted here in this picture. But the temperature at this node here is actually the average over the temperature of these neighboring points on the grid. And if you do that iteratively, you would actually get the final solution. And this can be done in analogy for the network. So here we cannot span a grid in a network topology, but we have nodes, and we regard the nodes as the points on the grid, and we have links, which is simply the interconnections in the grid. And so here the temperature or the potential value at node x1 would be the average over all its neighbors, which here are 4 nodes. So here just another explanation of the algorithm, how it works. Here is a simple example where you have a destination and a source. You just have one path. It's just to show how the algorithm will converge. You have at the beginning, you have the destination which has a temperature of 1, and all the remaining nodes have a temperature of 0. And then on the next iteration step, so this could be similar to when you have a distance vector routing protocol. You have periodically each node will actually send send a packet saying, including the distance information towards the destination. So this could be also implemented in this way. So every node periodically sends a broadcast to its neighbor its temperature value, and all the nodes that are in the neighborhood would actually use it and compute their own temperature according to this. So here, this node here on the iteration 1 has actually a value of 0.5 because he received the packet from this node and from this node, and he calculated the average, so it's 0.5. So this node is still a 0 because here this neighbor sent him a 0 and this neighbor is 0, so it has a 0. But on the next iteration step, it gets from this neighbor, it gets a 0.5, from this neighbor it gets a 0, so it has 0.25. And at the end, when you do that a couple of times, you get the final solution where you can see that the temperature at all the nodes is simply the average of all the neighbors they have. So we did a simulation study to understand what you gain actually by using link diversity routing versus shortest path routing, and this result is for a simulation study using a detailed map of the city of Zurich, so in Switzerland. So we actually took a map of the center of the city, 10 kilometers and 10 kilometers, and we base our mobility model based on this map. So that means that we pick a random point in the map and then a random destination, and the node will move according to the streets to this destination using the shortest path. Well, the simulation results are based on a modification of distance vector routing protocol for ad hoc networks, which is DSDV. So we take actually the DSDV routing protocol and modify in such a way that it actually calculates temperature values as I showed before, instead of using the number of hops as a path metric. And we compare actually the performance we get using this modification, using the heat analogy and the temperature compared to traditional shortest path distance DSDV. So this means that actually the overhead of both protocols, of both approaches is the same, because we do not add any new control messages. It's simply every node periodically sends distance. So here we have on this plot, we have here on the x-axis we have 3 different scenarios. We have the static scenario where all the nodes are fixed, well they are just placed randomly and they do not move. Then they can move at the pedestrian speeds, and the third scenario is when they move at car speeds in the city. And well, you can see when the network is static, you don't gain anything. But when there is mobility in the network, using the link diversity significantly improves the packet delivery ratio, because this is exactly what I shown before. You can actually, when a link breaks and you didn't envision that and you went over the shortest path, then the link breaks and you have to drop the packets. On the other side, if you use the link diversity, you have more forwarding opportunities.
So, question, how many nodes give you 100% PDR in 100 kilometers square? How many static nodes give you 100% PDR in 100 kilometers square?
I think for the simulation we varied the number of nodes between 200 and 2000. But these are ideal situations. So it's really a simulation. So we do not have for this we do not have.
Is that what 802.11?
Yes. So these are simulations done with GlomoSim. This is what we get from GlomoSim. So it's not, if you have interference from external sources and so on, you will have higher packet delivery, higher loss rates, but this is not accounted in the simulations. So what's interesting here is that actually here we used a larger number of nodes to get a node degree on average of 11. So every node has on average 11 neighbors. And here we decrease the number of nodes to get, for the same network size, to get an average degree of 5.5. So what you can see here is that the shortest path routing is not really affected by increasing and decreasing the node degree. So the result is pretty much the same, but the performance of link diversity routing decreases as the node degree decreases. And this is because simply if you have less nodes, the network is less dense, then you have less links, and then you also have less link diversity, because obviously if you decrease it even further, then this curve will converge to this one, because you might only have one path towards the destination. So there's nothing to optimize in this scenario.
And this is like flooding citywide to distribute that kind of information.
Yeah, this is actually the DSDV routing protocol. Yeah. So to conclude, there are three major things to conclude. Well, first, the field-based routing is actually, we view it as a simple framework that allows you to experiment different routing strategies, as I've shown in the talk. The nice things about the framework is actually that you have a guaranteed delivery if you manage to establish a potential field that has no local maxima, and you get loop freedom. So you can guarantee there is no loops in your routing. And these are actually two nice properties that any routing protocol must have. Then applying this model to AnyCast routing, we're able to actually instantiate or to implement a new routing strategy, which is density-based AnyCast routing, and we show that it's actually more robust than traditional shortest path AnyCast routing when you have dynamics in the network. And the best trade-off is actually not using only the density, but using a combination of the proximity and the density. And regarding, we have also used the model, the field-based routing model, to implement link diversity routing, and we have also seen that it's more robust than shortest path Unicast routing, and it can using this method in analogy to the finite difference method, you can actually determine the temperature of all the nodes using only the information from your direct neighbors, so you only need local interactions to implement the protocol. That's it.
For a static